Okay. Are you able to see the slide?
Yes, sir.
Yes, sir.
I'm changing. Please confirm you are seeing the change.
Yes, sir.
Okay. Let others join. We'll get going. Welcome to Department of Chemical Engineering, Banasthali Vidyapeeth. We are on THE 305 Chemical Technology Lecture 27. In the last lecture, we saw the politics and economics behind petrochemicals, the red hot industry. Just to have a brief, crude oil and natural gas are the primary raw material for production of most bulk organic chemicals. Bulk organic means from which hundreds and thousands of more products are made. The first stage in the petrochemical industry is conversion of these raw materials into base chemicals. Right? Lower alkene typically these are the base chemicals, which are classified as lower alkene, which includes ethene, ethylene, propene, propylene, and butadiene. Aromatics, benzene, toluene, xylene, BTX. Then syngas. Syngas is a mixture of hydrogen, carbon monoxide, some ammonia, methanol. Right? So these are all the things which we have to do first before going further. Right? See, almost all aliphatic compounds can be made from all these ethylene, propylene, butadiene. And almost all aromatic compounds can be made with benzene, toluene, xylene. And hydrogen, carbon monoxide, ammonia, methanol, again, we can reach out to ammonia, to urea, and many more, right? So, like that. Hydrogen and carbon monoxide can be used to make methanol, right? So, we have a whole option starting with this point. Then the lower alkenes are mainly produced by steam cracking of ethane or naphtha, while aromatics are predominantly produced in the catalytic reforming process. This you have already seen in the petroleum refinery. What is cracking, hydrocracking, and reforming? Remember, hydrocracking will not be suitable for petrochemicals. You know the reason. Because, in hydrocracking, because cracking is done in the presence of hydrogen, any ethylene, propylene produced will all get saturated to ethane, propane. Right? So, steam cracking, normal catalytic cracking, FCC, would be the best to make ethylene, propylene, etc. Syngas, which is the feedstock for ammonia, carbon monoxide, and hydrogen, with which we can make ammonia, I can make methanol also, is predominantly produced by steam reforming of natural gas and also partial oxidation. This we have seen in the beginning in the hydrogen chapter itself. Then in the second stage, so this is the first stage. Then in the second stage, a variety of chemical operations is conducted, often with the aim to introduce. Now I make heteroatom. I bring in oxygen, chlorine, sulfur into the molecule. Right. So ethylene, I bring in oxygen to make ethylene oxide like that. Right. Or ethylene, I put chlorine to get, vinyl chloride. Right. So first stage is produce these, and in the next stage bring in the heteroatom, oxygen, chlorine, sulfur, like that. This leads to the formation of chemical intermediates. So these are your base chemicals. Then with the addition of these things, you get whole lot of intermediates. We get acetic acid, formaldehyde, ethene oxide, ethylene oxide, and monomers like acrylonitrile, terephthalic acid, and so on. It goes on and on. A final series of operations, often consisting of a number of steps, is needed to obtain advanced chemicals, industrial specialties, and consumer products. And these products include plastics, polyvinyl chloride, PVC, polyacrylonitrile, synthetic fibers, polyesters like polyethylene terephthalate, PET, nylon 6, elastomers, for example, polybutadiene, paints and coating, herbicides, insecticides, fungicides, these are all agrochemicals, fertilizers, ammonium nitrate, vitamins, flavors and fragrances, soaps, detergent, cosmetics, consumer chemicals, and pharmaceuticals. Look at this. So we can go into a amazing set of products. You just see, where we could start with gas, natural gas, or crude oil and other hydrocarbons, right? So I can go out to reach, get various alcohol, and from butane, I can make malic anhydride, and from malic anhydride, I can make fumaric acid, and from syngas, I make methanol, and from methanol, I can make formaldehyde, right? And you can see how many more: methyl formate, methyl chloride, ethanol, acetic anhydride, methylamine. Then with ammonia, I can make many amine, urea, nitric acid, ammonium nitrate, right? So if you see this figure, and from here you see you get aromatic, you know, this is a small thing which tells what happens in the refinery. One aspect of refinery reforming produces aromatics: benzene, toluene, xylene. See, with benzene, I can make cyclohexane, then caprolactam nylon, like laurolactam, and adipic acid. Adipic acid, nylon 6,6. And with benzene, I can make ethyl benzene, and then styrene, and then polystyrene. Then I could make acrylonitrile, right? And with phenol, I can make styrene, SAN, another polymer, right? With cumene, right? Phenol, I get aniline. From cumene, I get aniline. What is this? Alkyl benzene. Cumene and alkyl benzene, yes. You look, where, what else? Toluene. Toluene is phthalic anhydride, right? I can go to many more products, right? Dimethyl, what is this? Paraxylene, orthoxylene. So xylene, no, orthoxylene or paraxylene, and metaxylene is also there. Ortho and para, I can reach out to a whole lot of chemicals. Then from here, I can come to ethanol, polyethylene. So you see this figure from, I can make vinyl chloride, polyvinyl chloride, isopropanol, methyl isobutane, right? And methacrylic acid. I can get all these products. So you can see that this is, like I won't say it is a tree, it is a jungle, right? So to get the hang of petrochemicals, we start with C1 chemicals. That is one carbon. Methanol, formaldehyde. Methanol, is CH3OH. Formaldehyde is HCHO. Chloromethane. There are four of them. Methyl chloride, CH3Cl. That is, on methane, I do chlorination. So one hydrogen is replaced, I get methyl chloride. Two hydrogen replaced, I get methylene chloride, CH2Cl. Three hydrogen replaced, I get CHCl3, chloroform. All four hydrogen and methane substituted by chlorine, I get carbon tetrachloride, CCl4. CCl4. Let's start with methanol. Methanol manufacture is something very similar to ammonia making. Right. So in ammonia, we do carbon monoxide. What is it? Hydrogen and nitrogen forms ammonia. Whereas for methanol, the raw material is carbon monoxide and hydrogen. In the reforming, we do get carbon monoxide and hydrogen. Right. Of course, we will not be doing the shift reaction for methanol making, because the reason is obvious. Shift reaction will, use the CO, right? So it will be typically primary reformer, secondary reformer, then CO2 removal, and then I have a mixture of carbon monoxide and hydrogen, which goes for making methanol. It is an exothermic reaction. Or some carbon dioxide present may also react with hydrogen to form methanol, also exothermic. These are the two methanol forming reactions. They are coupled by the water gas shift reaction, right? So carbon monoxide may react with water to form carbon dioxide and hydrogen, right? So these are the main reaction is a possible side reaction. Then the first industrial plants were based on a catalyst that was fairly resistant to impurities, but not very active nor selective, and was operated at high pressure. So the reaction was carried out at high pressure, 300 atmospheres, and many byproducts due to side reactions came. So methanol making was not all that easy initially. Then came a major breakthrough in the late 1960s with the development of low pressure process. Remember, here it was 300 atmosphere, then we reached low pressure, and we had more active and selective copper-based catalysts. Right? So modern processes for methanol making uses copper-based catalysts. All modern processes are low pressure with plant capacities ranging from 150 to 6,000 tons per day. Although plants using remote natural gas may have a capacity as large as 10,000 tons per day. It's huge methanol plant. In the ICI process, right? So this is the development of the low pressure process. It was developed by a company ICI, which doesn't exist now. It has got name changed and merged, right? So ICI pressure 35 to 54. Imagine coming down from 300 atmosphere to 35 to 54 atmosphere, temperature 200 to 300 degrees centigrade. Then adiabatic reactor is used with single catalyst bed. There's just one single catalyst bed, not like the sulfuric acid in which 3 or 4 trays of catalyst is kept. The reaction is quenched by adding cold reactant gas at different heights. Remember, the reactions are exothermic. So the catalyst keeps getting heated because of the reaction. And what is done is the cold raw material is not injected into the reactor in one point. It is spread, throughout, so that at different places it will take away the heat, right? So that is a strategy in reactor design. Fresh syngas is compressed and mixed with recycled gas because the reaction does not go to completion. So the unreacted raw material, similar to ammonia making, right? Unreacted raw material, carbon monoxide and hydrogen, must be recycled back. The mixture is heated with reactor effluent, and because the products are hot, right? So the raw material, cold carbon monoxide and hydrogen is heated, right? Subsequently, about 40% of the stream is sent to the reactor after undergoing supplementary preheating also by the reactor effluent. The rest is used as quench gas. Quench gas means, that is, I am not putting the entire carbon monoxide hydrogen in one place in the reactor. Part of it goes into the reactor and remaining is put at different point in the reactor bed. The reactor effluent is cooled by heat exchange with the feed and with water required for high pressure steam generation, and then by passage through an air cooled exchanger in which the methanol and water are condensed. Gas liquid separation is carried out in a vessel under pressure. The gas is recycled after purging a small part to keep the level of inerts. Some argon nuisance is likely to be there. So entire recycle is not recycled. A small part is purged out in the loop within limits. The crude methanol is purified in 2 columns. The first column removes gases and other light impurities. The second separates methanol from some heavy alcohols, side stream and water. Because remember that the side reactions may lead to formation of higher alcohols than methanol also. The flow sheet is here. The syngas. Syngas is carbon monoxide and hydrogen. It enters through a heat exchanger, and the product from the reactor is hot, and some steam is raised, and the gases pass through the heat exchanger, heating the incoming raw material. Incoming raw material, you see, it goes here, split into multiple stages, right? So we are not putting the entire thing in a reactor because the reactor bed will hot and then cooling will become a problem. So I am putting it at different points so that the heat generated will get utilized, okay, and it will get quenched, right? And the hot gases, they are taken to a separator, right? A gas liquid separator, where the gas is meant for recycle. What is the gas? Carbon monoxide and hydrogen, right? Carbon monoxide and hydrogen will be recycled after heating, right? And mixed with the fresh feed. Okay, and the liquid goes to light end column where any lighter products or hydrocarbons are removed, and the heavier one goes to the methanol column where on top you get methanol and at the bottom you get other higher alcohols. Okay, so this is the flow sheet for the process, and remember that why we are putting it in multiple places is the catalyst is in one bed, right? So if I put all the raw material in one place, then the reaction will become hot and the bed will have to be cooled. So instead, I am putting the cold raw material in different parts of the reactor catalyst bed so that the cooling, quenching of the heat generated gets done. Okay, so this is a strategy behind this process. Two columns are there to remove the light in and then pure methanol, removing the higher alcohols. Then we also have a Lurgi process. Lurgi is another giant in cryogenic air liquid separation. Right, Lurgi process with a cool tubular reactor is very similar to the ICA process. A relatively new development in methanol is three-phase process invented by Chem Systems and developed by Air Products using a slurry reactor in which a solid catalyst is suspended in an inert hydrocarbon. Right. So remember this copper catalyst. Okay. So a solid catalyst is suspended in an inert hydrocarbon liquid while the syngas passes through the bed in the form of bubbles. Of course, there has been a lot of talk of, why from methane I make carbon monoxide, hydrogen, and then use carbon monoxide and hydrogen to form methanol. Why can't I make directly from methanol, from methane, methanol? Direct conversion of methane to methanol has been the subject of many academic research effort during the past decades, but today the low yield achieved is a major obstacle. So methane will react with oxygen to form methanol. This is an exothermic reaction, but the feasibility and viability is still being checked out. Okay, so that is about methanol, the very important product like ammonia in the fertilizer industry. Methanol is a starting point for many chemicals in the organic industry. And formaldehyde, HCHO, imagine the largest application of methanol is in making formaldehyde. Account for 35% of methanol consumption. Formaldehyde is made, the synthesis of formaldehyde, which is based on one of the reactions. So methanol can dissociate into CH2O plus H2O. This is the same. CH2O is HCHO, right? Or methanol can combine with oxygen to form formaldehyde also. There are two reactions. One is endothermic, the other is exothermic. Formaldehyde can be produced by dehydrogenation or by partial oxidation. This is partial oxidation, right? The former is endothermic, while the later is exothermic. As should be expected, several side reactions take place in industrial practice. Dehydrogenation and partial oxidation are often carried out over a silver-based catalyst in a single reactor in which the heat produced by exothermic reaction supplies heat for the endothermic dehydrogenation. So both reactions are happening simultaneously, right, where the heat generated supplies heat for the heat required for the other reaction. Okay. Fresh and recycled methanol is evaporated in a vaporizer into which, remember, the reaction doesn't go to completion. So after separation, the methanol must be recycled back because that is the main raw material. So the resulting vapor is combined with the steam and heated to the reaction temperature. The reaction takes place in a shallow bed of catalyst. Remember, what is the catalyst? Silver. Silver-based catalyst. Okay, and after cooling the gases, the gases are, after cooling, the gases are fed to an absorber and distillation yield 40 to 55% weight of formaldehyde solution in water. And methanol is recycled to the vaporizer. Overall reaction is highly exothermic because this is endo, this is exo, overall is exo, right? Despite some heat consumption by the endothermic reaction. Because it occurs at essentially adiabatic condition, good temperature control is critical. This is mainly achieved by use of excess methanol. So excess methanol is used, which is recycled and by the addition of steam to the feed. So flow sheet is simple. I feed in methanol, air, and steam heating, right? This for supplying heat, and again steam is added, right? Then it goes to the reactor where a silver catalyst bed is there, 10 to 50 millimeter thick catalyst, right? So reaction temperature is 1.5 atmosphere bar and 890 K, and the reaction is exothermic. So water forms steam. BFW stands for boiler feed water, which means demineralized water, right? So because the heat must be taken from the reactor, so the water circulation becomes steam, and the heat is, exothermic heat is taken out, and then it goes to the next stage after cooling, right? The light gases are let out, the water wash, and then goes to methanol distillation column. This is an absorber where water is being added, right? And then the methanol column, the product formaldehyde is got. And the bottom product is formaldehyde, and the top product is the unreacted methanol, which is recycled back to the system. So this is about formaldehyde. A process about equal industrial importance is based on the partial oxidation reaction over a metal oxide catalyst. In addition, in contrast to the silver catalyst process, this process operates with excess air, right? Remember, this process operated with excess methanol, right? So, different catalyst uses with excess air, and therefore it has the advantage that the distillation column for methanol recovery can be omitted. This will completely be not there because methanol becomes the limiting reagent and air is the excess reagent. So, all methanol will get finished up. So the methanol conversion is over 99% in this proposed new process with a metal oxide catalyst. So for advances in methanol conversion to product, you are welcome to read this reference where a lot of interesting products are there. I leave it as a reading assignment to you. Okay. Then comes manufacturing process of chloromethane. Chloromethane, methyl chloride, CH3Cl, methylene chloride, CH3Cl2, chloroform, this CH2Cl2, right? And chloroform, CHCl3, and carbon tetrachloride, CCl4. This is CH2 produced by direct chlorination of chlorine. Now you see, methane plus chlorine form methyl chloride, and one hydrogen is removed, combined with chlorine to form HCl. And in methane, one hydrogen has been substituted by chlorine. Then methyl chloride reacts with more chlorine to form methylene chloride, second one, and HCl. Methylene chloride with more chlorine form chloroform, that is CHCl3 plus HCl. Chloroform reacts with chlorine to form CCl4 and HCl. Okay, the reactions are very exothermic. The feed molar ratio affects the product distribution. This is a very interesting case of, what to take excess and what to take as limiting, right? When methane chlorine is about 1.8, then more methyl chloride is produced. That means what? Right? I am having excess methane. So when I am having excess methane, all my chlorine will be targeting methane, right? And it will have a reduced chance of chlorine hitting the methyl chloride. Okay, so you see that by taking excess chlorine, 1.8, see, this is 1:1. So if I take 1.8 to 1, I'm ensuring that the excess methane ensures that methyl chloride formation predominates. So the chlorine will have less chance to hit a methyl chloride to form methylene chloride. Right. So if you choose methane as the limiting reactant, suppose you take excess chlorine and methane is the limiting reactant, then you will see that carbon tetrachloride formation will be more. Okay, so this is a very interesting case. If I want this as excess, this as the product, I should take methane as excess reactant. If I want carbon tetrachloride as a product, I should take chlorine as the excess. Okay, so very interesting combination. And depending on the proportion you want others, then this methane chlorine ratio can be adjusted. So you will see that whatever you do, all the four products are getting produced, some in large quantity, some in small quantity. Right? Let's see how the process works. Methane and chlorine are mixed and sent to a furnace. Methane and chlorine are mixed and sent to a furnace. The furnace has a jacket, right? These are exothermic reactions. The furnace has a jacket or a shell and tube system to accommodate feed preheating to desired furnace inlet 280 to 300 degrees. To control the temperature, nitrogen may be used as a diluent at times. Nitrogen acts as a diluent and inert to keep the furnace heat taken away. Right. Depending on the product distribution desired, the methane chlorine ratio is chosen. So you saw an example. If I choose 1.8, more methyl chloride. If I choose chlorine in excess, then I find CCl4 is maximum. Right. So depending, the product gas enters in a integrated heat exchanger that receives separated methane or a mixture of methane and nitrogen and gets cooled from the furnace. So eventually the mixture enters an absorber where water is used as an absorbent and water absorbs the HCl to produce 32% HCl. Remember, the HCl produced is absorbed in, HCl is in a gas form, so the water will, absorb the HCl to produce 32% HCl. The trace amounts of HCl in the vapor are removed in a neutralizer filled with NaOH. So I'll give a caustic wash so that any leftover HCl will get be neutralized. Okay. Then the gas is compressed and sent to a partial condenser followed by a phase separator. Phase separator produces two streams, a liquid stream consisting of the chlorides and the unreacted methane nitrogen. Right. Nitrogen, remember, we use it as an inert and a diluent. Right. The gaseous product enters the dryer to remove water from the vapor stream. Drying is done using 98% sulfuric acid as the absorbent for water from the vapor. Chloromethane enters the distillation sequence. Remember, there are four chloromethanes: methyl chloride, methylene chloride, chloroform, and carbon tetrachloride. So it goes through a sequence of distillation to remove them one by one because their boiling points and relative volatility differ. The sequence consists of columns that sequentially separate the methyl chloride, methylene chloride, chloroform, and carbon tetrachloride. Remember, it's an interesting thing that if carbon tetrachloride I do pyrolysis, then I get perchloroethylene. Perchloroethylene is formula Cl2C double bond CCl2. It's like all the hydrogen in ethylene has been replaced by chlorine. Right? It's a dry cleaning agent, dry cleaning solvent. So look at the flow sheet for the manufacture of chloromethane. I have methane and chlorine. Recycle brings me methane because I am taking excess methane, right? And chlorine. So go to the reactor. So check what is the catalyst that is used, chloromethane. No catalyst is there. Goes to the reactor, right? And the preheated feed is fed back, and then goes cooling absorbent. A water wash is given so that HCl gas is absorbed in water and forms 32% HCl. Then some carryover HCl may be neutralized with caustic soda, and then this goes to a condenser, right? From where it goes to a drying tower, because water has to be removed. Using sulfuric acid, we do the drying, and the product now, you have all the four chloromethanes in together. I put to a distillation column, multi-component fractionation like the crude oil atmospheric column. I get this is heavier carbon tetrachloride, then chloroform, then methylene chloride and methyl chloride. Right. These light ends can be further chlorinated if nitrogen recycle is not used. Okay. So that is about the C1 chemicals. Now we move into C2 chemicals. C2 chemicals. C2 chemicals, you have ethylene. In fact, when we make ethylene, some acetylene and propylene also simultaneously get produced. When we see the flow sheet, you will see. Ethylene oxide, ethanolamine. Remember, ethanolamine we talked in the ammonia manufacture, where CO2 removal is done by monoethanolamine or diethanolamine, MEA, DEA. Then ethylene glycol, vinyl chloride, ethyl alcohol. Although ethyl alcohol, the main route is by the fermentation of the molasses in the sugar plant. Petroleum route can also be used for making ethyl alcohol. It doesn't rule out, but may not be preferred. Then trichloroethylene, acetaldehyde, acetic acid, acetic anhydride, vinyl acetate. So you have a whole lot of C2 chemicals, and we have just picked up this lot for further briefing. Okay. Most likely in today's lecture, we will be able to see through ethylene, ethylene oxide, ethanolamine, ethylene glycol, vinyl chloride, and ethyl alcohol. And probably in the next lecture, we will cover the remaining and go to C3 chemicals. Now let's start with ethylene, C2H2. The most coveted petrochemical, ethylene. Ethylene is a critical building block for the petrochemical industry. It is among the most produced organic compounds. It is usually produced in steam cracking units from a range of petroleum-based feedstock. You recollect the naphtha cracking, fluid FCC, etc., where we could take various fractions, probably except the vacuum distillation heavy one, we could steam crack many of the other fraction naphtha, etc., and is used in the manufacture of several major derivatives. Ethylene is the most produced organic compound globally and is an important building block for the petrochemical and chemical industry, with over 150 million tons of ethylene produced yearly. Wow. Ethylene plants can use a wide range of hydrocarbon feedstocks. One of the most common type is naphtha, a mixture of hydrocarbons that has a boiling range of 30 to 200 degrees C, that is 86 to 392 F. In some regions, including the United States and the Middle East, ethane and propane are the most commonly used feedstock for ethylene production. So many places naphtha, but USA and Middle East, they use ethane propane also as the feedstock for ethylene production. The rapidly growing production of shale gas. I told you, shale gas is something similar to the seashells you find, and which when buried, they form, shale gas, right? So most of the ethylene produced is used in the production of polyethylene, which we'll see in the polymer reaction, and ethylene oxide, which is a feedstock for many more complex hydrocarbons. So ethylene can be made to polyethylene. On polyethylene, you have low density, high density, etc. And ethylene can also be made into ethylene oxide. And ethylene oxide is a raw material for many more complex hydrocarbons and polymers. The main commercial production of ethylene is by either thermal cracking or steam cracking. We have already seen that thermal cracking is not preferred, right? And steam cracking is what is preferred using a catalyst, right? A different hydrocarbon feedstock, which is typically divided into few main steps. The operations can be cracking, quenching, compression, and drying and separation. Right. So let's see each of them. Cracking and quenching. Initially, an ethane propane mixture is led to furnace. So we are taking the raw material as a mixture of ethane propane, right, and not naphtha. Right. Naphtha can also be used instead of ethane propane. Ethane propane mixture is fed to furnace in which under high severity conditions it is cracked, forming ethylene, propylene, and other byproducts. The furnace outlet stream is subsequently fed to a water-based quench to prevent further reactions and formation of undesirable byproducts. From a decanter downstream, from the quench jar, heavies, condensed solution, and coke are removed. Some coke formation happens. Cracked gas from the quench is then directed to compression and separation. The next stage is compression and drying. The compression of the cracked gas is performed across 5 stages. After the third stage of compression, that is, compression is done stage-wise, right? So 5-stage compression, of which after third stage, carbon dioxide and sulfur are removed from the cracked gas by caustic soda and water washes in a caustic scrubber, right? And the compressed cracked gas is cooled and subsequently dried by molecular sieve that removes most of the water. So compression and drying. And last comes separation. The dried cracked gas is fed to a cold box for removal of hydrogen and lighter hydrocarbons while minimizing ethylene loss. At this point, the condensate from the chilling train are fed to a series of separation columns. So the first column is demethanizer. Remember, we are done in the process synthesis in separation task selection, an example for this problem situation we are discussing. Demethanizer, and then methane is obtained from the top and further used in the cold box, while the bottom stream is fed to a second column, de-ethanizer. So first remove methane, then ethane, and then the top of the ethanizer primarily has ethylene and ethane and fed to an acetylene converter and then fractionated into C2 splitter. Right, C2 splitter means ethane ethylene splitting is known as C2 splitter. In this column, lights are removed from overheads and recycled to the compression system, while polymer grade PG ethylene is drawn from the column as a side stream. Ethane from C2 splitter bottom is recycled to the cracking furnace. Right, so unreacted ethane. So the de-ethanizer bottom stream is fed to a de-propanizer, which distills the C3 components in the overhead. Right. So then when we see the picture, it will all be clear. This overhead stream is catalytically hydro-treated for methyl acetylene and propylene removal and then fed to the C3 splitter. In this column, lights are removed from the overhead and recycled to the compressor, while polymer grade propylene is drawn from the column as a side stream. Propane from C3 splitter is recycled to the cracking furnace. C4 plus stream is obtained from the depropanizer. Let's come to the figure. Oh, yes. You have the feed is a mixture of ethane and propane, right? Ethane and propane goes to a furnace, right? And then goes to what is the next stage? Cracking column, right? So from here, then it goes for compression, multiple 5-stage compression. This symbol denotes compressor. 5-stage, 1, 2, 3, 4, 5. After the third stage, we have already discussed, right? It then goes to a 4th and 5th stage, right? And then the lighter one go for fuel, and then we have a series of separation tasks. like see, you can see this is the description of various columns are all given here, right? Then we get polymer grade ethylene product after a series of separation, right? So we also get some propylene is formed in cracking. So C3 splitter will get you the propylene, and some C4 plus is also brought in, right? So the entire sequence now gives you some ethylene, propylene, and also heavier one, C42 fuels. Then with a more elaborate flow sheet of what you have seen here, right? To understand this, you could see this reference, right? The same figure which is given there, right? So to catch up with the starting point, with the starting point. These are all removals. This C2 splitting, C3, acetylene, propylene. So please click this reference to get a more elaborate picture, but it's the same sequence which we have discussed here. Then comes ethylene oxide, a very important chemical in the organic industry. Ethylene reacts with oxygen to form ethylene oxide. Look at the structure of ethylene oxide. CH2CH2O, cyclic. Two CH2 joined with a carbon, with an oxygen. Heteroatom has come into picture, right? So ethylene reacts with oxygen to form ethylene oxide or ethene oxide, right? So how do we do it? It's an exothermic reaction. Catalyst is the problem. Ethene oxide, because of its reactivity, is an important raw material for the production of a wide range of intermediates and consumer products. The main outlet for ethene oxide is the manufacture of ethene glycol or ethylene glycol, accounting for about 60%. Other uses are in the production of surfactants, detergent, ethanolamines, and so on. And after polyethylene, ethylene oxide is the second largest consumer of ethane. Direct oxidation of ethene has largely replaced a more complex route to ethene oxide. Okay, so originally ethane oxide was produced by indirect oxidation of ethene via ethene chlorohydrin, but right now the basic reaction is you have ethylene plus oxygen forming ethylene oxide, exothermic reaction. Coming to the flow sheet there, right? Coming to the flow sheet there, I have ethene, that is ethylene, and small quantity of methane is added, right? We'll see the purpose for which it is done, right? And oxygen. So the products are hot, raw material is cold. So I have a heat exchanger where the incoming raw material is heated by the hot product, cold raw material heated by hot product is a very common strategy in many industries, right? And the feed now goes to the reactor, right? Where the, what is this? Reactor, where steam is added, right? It is steam cracking, right? Then the products they go into a ethylene oxide absorber where light gases are removed, and from here I can remove in two separation columns some ethylene unreacted can be recycled back, and this can go to another column where carbon dioxide is also removed. Okay. Then here the bottom product goes through a heat exchanger and then come to a column ethylene oxide desorber, right? And next is light end column. Some of the lighter hydrocarbons are removed. Then it goes to the next column, last purification column, where ethylene oxide, water are separated. Okay. Now, the reaction, remember, ethylene oxide and oxygen. Instead of air, which has oxygen and nitrogen, inert and diluent, it is advantageous to use pure oxygen and methane as diluent, since methane has a higher capacity and thermal conductivity than nitrogen. Remember, if I had used air, my nitrogen will do the inert and what is that? Diluent job, right? Because you know the air will contain 21% oxygen and 79% nitrogen. Okay, so if I'm using air, my nitrogen is acting as an inert and diluent. But if I'm using pure oxygen, I will add a small quantity of methane to do the inert job because there is no nitrogen present in the system. The reaction is conducted at elevated pressure to facilitate the subsequent absorption of ethylene oxide in water. The gases leaving the reactor are cooled by heat exchange with feed gas and sent to a column where ethylene oxide, only present in concentration of 1 to mole percent, is absorbed with water. Okay. Then the aqueous solution, which is rich in ethylene oxide, the solution is rich in ethylene oxide. Where we, yes. So now you know why methane is added. Because I'm using oxygen, there is no inert nitrogen present there. So to compensate it, I'm adding a small quantity of methane to do the job of nitrogen inert for diluent, etc. Okay. Methane has higher heat capacity and thermal conductivity than nitrogen. That is to our advantage, which results in better isothermicity. Although the pressure has been shown not to influence the conversion much at typical reactant temperature, the reaction is conducted at elevated pressure, higher pressure, to facilitate the subsequent absorption of ethylene oxide in water. Then the gases leaving the reactor are cooled by heat exchange. The feed gas that I told you, the common strategy, products are hot, raw material is cold. So heat exchange, raw material gets heated and the product gets cooled. About 1 to 2 mole percent is absorbed in water. The aqueous solution rich in ethylene oxide that leaves the bottom of the ethylene oxide absorber passes through a stripping column, EVO desorber, right, separating the ethylene oxide at the top. The bottom stream has water and some ethylene glycol, which is formed when ethylene oxide comes in contact with water. This is returned to the ethylene oxide absorber. Now, what is the proportion? Ethylene and oxygen in certain proportion form explosive mixture. Whoa, we are not making a bomb. Okay, The feed to the reactor contains 20 to 40 mole% of ethylene and 7 mole% oxygen to produce the reaction mixture that is always above the upper flammability limit. This is one of the important characteristics of hydrocarbon, flammability limit, right? At what condition it will form vapor to get ignited, right? Immediately, upper flammability limit. The presence of carbon dioxide, which is formed in the combustion reaction, this helps to reduce the flammability limit. Oh, that's nice. Carbon dioxide produced helps to reduce the flammability limit, and therefore, not all carbon dioxide is removed from the recycle stream. Right? Some carbon dioxide is recycled back to the system. Depending on the amount of inert recycle, methane can be added in order to reduce the oxygen concentration and thus the flammability zone. Then comes another set of important product known as ethanolamine, very powerful solvents used in the industry. Right? They are excellent absorbers of carbon dioxide, of H2S, right? So irrespective of whether it is needed for purifying a gas or raw material for the synthesis of fine chemicals, the range of application for ethanolamine is very diverse. The mostly utilized feature of ethanolamine is what is so special about the ethanolamine? The surface tension reducing effect. It reduces the surface tension, which enables the mixing of water soluble and water insoluble substances. Wow. There are three different ethanolamine: monoethanolamine MEA, diethanolamine DEA, triethanolamine TEA. China T. Monoethanolamine is used primarily for extraction of carbon dioxide and H2S from natural gas. Diethanolamine is employed first and foremost for organic synthesis. 85% of triethanolamine serves, among others, as an additive in the cement industry. Wow. Okay, now look at this reaction. Ammonia reacts with ethylene oxide. Remember, ethylene oxide is CH2O, CH2, the cyclic. Right? These are the reaction engineering concepts. K1, K2, K3, three reaction. I form monoethanolamine. That is, the chain opens and ammonia gets in. And monoethanolamine reacts with ammonia to form diethanolamine. And diethanolamine reacts with more ethylene oxide, right? Monoethanolamine with one more ethylene oxide becomes diethanolamine. And diethanolamine with one more ethylene oxide becomes triethylamine. That is a MEA, this is MEA, next is DEA, and the third one is TEA. So in short, E plus A. E is what? Ethanolamine. So I am using E as ethylene oxide. Sorry, E is ethylene oxide and A is ammonia. E plus A forms M. E plus M forms D. E plus D forms T. So for just better understanding, I put the reaction here. So you see, one NH2 has got into it by opening this cycle. So monoethanolamine, right? So similarly, then I'm adding one more CH2O, right? So NH2. So one more hydrogen, right? In see, remember, just see what's happening. Out of this NH3, one hydrogen opens up and NH2. Then one more CH2. One more ethylene oxide comes and sits. Monoethanolamine, diethanolamine, triethanolamine. Okay. So this is an amine. There are two there, diamine. The three, triamine. Let's see the process flow sheet. Very simple and interesting, right? I'm having ethylene oxide and ammonia. They are put into the reaction, right? And the unreacted ammonia is recycled back, right? And this is your ammonia stripping, where the unreacted ammonia is put back, and the product go for a water wash, right? And amine solution dehydration, and then I go through a series of separation by which I get monoethanolamine. Then in the second tar, I get diethanolamine, and the third tar, I get triethanolamine and two grades of triethanolamine, right? Then come ethylene glycol. Ethylene glycol, CH2OH2. Monoethylene glycol is also known as ethylene glycol or simply glycol. Glycol means by default monoethylene glycol. Is a diol, two alcohol, OH twice, right? Mostly used for production of polyester fibers. Ethylene glycol is a very important thing for the textile industry for making polyester, right? So we'll come later, right? And polyethylene terephthalate. So for making polyester, polyethylene terephthalate, ethylene glycol is a very vital chemical. It is also used in antifreeze applications and in pharmaceuticals and cosmetics. Monoethylene glycol is conveniently produced through hydrolysis of ethylene oxide EVO, just ethylene oxide EVO, which itself is obtained via ethylene oxidation. Wow. Ethylene glycol production and purification. Ethylene oxide is reacted with carbon dioxide, forming ethylene carbonate, which is then hydrolyzed to form monoethylene glycol and CO2. Both reactions are carried out in liquid phase using a homogeneous catalyst. Carbon dioxide stream from the reaction steps are recycled to the ethylene carbonate reactor. Monoethylene glycol is purified and in two distillation columns where water is removed, leading to the final product. Catalyst is separated and recycled back. Just simple flow sheet, ethylene, oxygen. So this is actually a picture which is combining the manufacture of ethylene oxide, right, which we have seen, ethylene oxide, right, and ethylene glycol. So this part of it is ethylene oxide manufacture. Okay, so this we have already seen, ethylene oxide manufacture using ethylene and oxygen. And from here, I do my, I add carbon dioxide and my ethylene glycol reaction starts. This part is the flow sheet for ethylene glycol. Okay. So these are some of the important chemicals. You can see that ethylene, how important it is, not only for the manufacture of polymer polyethylene, it is also useful for ethylene oxide, ethylene glycol, right, and ethanolamine, right, all major products, they're all coming there. Next comes vinyl chloride. How we can forget it? Remember in lecture 4 in the course, we had thrashed out several vinyl chloride in process synthesis. The acetylene route, ethylene route, ethane route, etc. Right. But I am not going to go back into that. You go back and read it up, but we will take up where we left there. We arrived at a balanced process is what is recommended for vinyl chloride, and the process chosen for vinyl chloride is a combination of two, direct chlorination and oxychlorination. This process is referred as a balanced process. See, direct chlorination is one option, oxychlorination is another option, but the real thing is that a blend of these two is taken, which is known as balanced process. Direct chlorination by itself is a process that operates at low temperature and produces fewer byproducts when compared to oxychlorination. Oxychlorination is used in vinyl chloride because it consumes the hydrochloric acid. Right. So that otherwise it becomes a nuisance. What will you do with the HCl? Right. So that is why the direct chlorination and oxychlorination are done. You look at the reaction in direct chlorination, ethylene reacts with chlorine to form this product. Then oxychlorination. This is ethylene dichloride, right? So chlorine has got added over, right? One chlorine on this double bond and one chlorine on the other double bond. And this is a direct chlorination reaction. Then this undergoes pyrolysis to give you vinyl chloride and HCl. Now, this is my direct chlorination route, right? Ethylene plus chlorine forms dichloro, uh, clean dichloride with EDC, right? And by pyrolysis, this is EDC. This product is EDC. EDC pyrolysis gives me vinyl chloride and HCl. What do I do with HCl? So I am using oxychlorination, where ethylene combines with HCl and oxygen to again form this EDC, so that my HCl is consumed. And I combine all, my overall reaction is this, right? So 2 ethylene plus chlorine plus oxygen, I get 2 vinyl chloride, VCM. It is known as vinyl chloride monomer. It's a very important product for making polyvinyl chloride, right? So for more details, you may see this reference. The 5 main steps used in the production of vinyl chloride by the balance process are direct chlorination, oxychlorination, then purification, thermal cracking of the EDC, right? These are the steps. Direct chlorination, then oxychlorination, then pyrolysis. Purification and thermal cracking of the EDC, right? So any purification is to ensure that unwanted material are removed. And the thermal cracking of EDC form VCM and HCl, and then the purification of VCM. VCM means vinyl chloride monomer. Okay, so you see air or oxygen, this is oxychlorination. A part of ethylene goes here, and this is direct chlorination, chlorine. So remember, the actual flow sheet of vinyl chloride, PFD stands for process flow diagram, right? So this is my direct chlorination, this is my oxychlorination. But in oxychlorination, I need HCl, which my direct chlorination will bring, and the HCl is brought here, right? Very nice. So EDC purification, the lighter ones are removed, and then the pyrolysis gives you my VCM. And here purification will give me any unreacted EDC, which I can put back. So this is about vinyl chloride monomer. I think we can, one last, ethanol. This is very interesting, just for academic sake, because ethanol is not made from ethylene. In fact, ethanol is made more by the molasses. Sugar industry fermentation will give me ethanol, right? So, but still, I cannot rule out that if my agricultural industry does not give me ethanol, where will I go? Suppose everybody stops eating sugar, then there is no sugar cane and molasses to form ethanol. By I can make my ethanol from ethylene, right? And you know how to make ethylene in the refinery, and ethanol is manufactured by reacting ethylene with steam. So ethylene with steam will give me, see the reaction, ethylene in gas form, steam, H2O forms ethanol, and that is a exothermic reaction, right? A simple flow sheet, 95% conversion, 1 volume of ethylene and 0.6 volume of steam. See, the stoichiometry says 1 is to 1. 1 ethylene and 1 steam gives me my ethanol. But why do I take 0.6? In fact, I should take steam in excess. I should take steam in excess. This is what will be the argument of you and me. But let's see why it is not done so. Why ethylene is taken, what is this, 1 volume, and H2O is 0.6. Ethylene is in excess and H2O is the limiting reactant. Rather, people would argue that steam should be in excess so that all the ethylene is finished. Why it is so? The reaction happens at 300 degrees, 60 to 70 atmosphere. Catalyst uses phosphoric acid. Make a note, phosphoric acid. Phosphoric acid. That means it contains water. Okay. Now, higher pressure is justified because there is a reduction in mole. 1 mole here, 1 mole here, and 1 mole here. 2 moles on the raw material and 1 mole on the product, which means higher pressure favors Leach Atlas principle. And I cannot get a decent conversion at low temperatures. I need 300 degrees. Fine. But why excess ethylene and not excess steam? The clue lies in phosphoric acid. The proportion of ethylene and steam, ethene is ethylene. Equation shows that ethene and steam should be 1:1. One ethylene and one steam. But we are doing 1 ethylene and 0.6 steam. Remember, this is limiting reactant and ethylene is the excess reactant. Why? In order to get this ratio, you have to use equal volumes of the two gases. But water is cheap. I would say that I will use excess steam, right? In according to the Leach Atlas principle, and in practice, an excess of ethylene is used. This is surprising at first sight. Even if the reaction was one way, you could not possibly convert all ethylene into ethanol. There isn't enough steam to react with it. The reason for this oddity lies with the nature of the catalyst, phosphoric acid. Look, if I take excess steam, it will dilute the catalyst phosphoric acid. This phosphoric acid is on a solid silicon dioxide support. If I use excess steam, my phosphoric acid will get diluted catalyst and it will get even washed away. That is why I am not using excess steam, right? So that my catalyst doesn't become a non-entity. So remember, this is a very peculiar case where logically you would have told this should be excess reactant, this should be limiting reactant, but in reality, this is excess and this is limiting because of phosphoric acid. Very interesting phenomena. Remember that technology allows you to discuss all these things and should have an open mind in understanding the flow sheet. Why this excess? Why this temperature? Why this pressure? Pressure, I told you that number of products is moles of product is less compared to number of raw material reactant. So like ammonia making, high pressure is favored. 2 moles on the raw material and 1 mole on the product. So higher pressure is favored. 60 to 70, tell ya. 300 because it is that temperature at which the reaction happens, to some extent. Then the unreacted material is recycled back. Okay. So that is it for the day, and thank you all. Thank you. We will take up the remaining C2 petrochemicals in the next lecture. Remember, the GATE exam has substantial focus on petroleum, petrochemicals. So please try to get a hang of the product, its uses, and catalyst use, etc. It is to your advantage. Okay, so thank you all. Thank you. Thank you.